In this segment, we're going to discuss functions of two or more variables. A good deal of this segment will just really be about feeling comfortable with the notation. So in section 14.1, rather than looking at functions like we usually do, say f of x equals x squared plus 1, or even f of y equals 2y minus 3, okay, we're going to be looking at functions of more than one variable. So, for example, we might have a function that depends, whose value depends on both an x and a y value. So, for example, we could have 2xy minus x squared minus y squared is a function of two variables. We could also have three variables. So for example, f of x, y, z equals x plus y plus z would be a function of three variables. Now there are different ways of visualizing these functions. It's important to mention, since we've just finished vector valued functions, that these are not vector valued functions, although in some cases their graphs will look the same. These are traditional functions, just depending on multiple variables rather than one. So in this first example, we're going to just practice using the notation. This is very similar to number 2 on page 937. We're given f of xy equals the formula x plus cubed root of xy. And in part A, I'm going to ask you to find f of 2, 4. Now, just like in an ordered pair, the order matters here. Whatever's in the first coordinate is going to match up with the x in the formula. Whatever's in the second coordinate, in this case 4, will match up with the y in the formula. So plugging in, we're going to have 2 plus the cubed root of 2 times 4. Now 2 times 4 is 8, the cubed root of that is 2, so we're going to have 2 plus 2 equals 4. So notice that the result of this function is a single real value. Let's try another one. Composition of functions will occur with functions of more than one variable, just as they have in the past. And we're going to look at those in more detail, but just to mention that this sort of is a composition of functions in that we're plugging two functions in for our x and our y. We're plugging t in for x and we're plugging t squared in for y when we say find f of t comma t squared. So going back to our original formula, wherever we have an x, we're going to put in a t. Wherever we have a y, we're going to put in a t squared. So this is going to be equal to t plus the cubed root of t times t squared, x times y. Well, t times t squared is t cubed. Cubed root of t cubed is t. So this is equal to 2t. Let's try another one. Part C. Now in this part, it's a little more confusing for people. You have to just be a little more careful, because notice that we're plugging x and x squared. We have the same variable appearing, at least one of the same variables appearing that we did in the original function. And so again, you need to remember that we're plugging in this item for x, so in other words, x is staying the same, and we're plugging in x squared for y. So this is going to be equal to x plus the cubed root of x times, and now y is really x squared in this case. So simplifying, again, this is going to be x cubed under the radical, so the cubed root of x cubed is going to be x, so we have x plus x is 2x. Alright, let's try one more. Part D. What if we had f of 2y squared, comma 4y? Well, in that case, Again, this we're plugging in for x, and this we're plugging in for y. So we're going to have, instead of x plus cubed root of xy, we're going to have 2y squared, where we had the x, plus the cubed root of 2y squared times 4y instead of y. Okay, well that's going to be 2y squared plus the cubed root of 8y cubed. So that's going to be 2y squared plus 2y. So notice that in this particular case, when we plugged in 2y squared for x and 4y for y, the result is a one variable function. Alright, let's try another one, part E. What if I asked you to find f of xy comma x squared plus y squared? Now we're not going to be able to simplify this very much, but the important thing is just recognizing what the notation means. So again, we're plugging in this wherever we have an x and this wherever we have a y. So we're just going to have xy plus cubed root of x times y is now going to be the cubed root of, we're plugging in xy for x, and x squared plus y squared for y. And again, I could distribute this. It's not going to do me a whole lot of good as far as being able to factor. So I'm just going to leave it in this form. Now in this case, plugging in this sort of composition here, because we were taking two variable functions, plugging into this two variable function f, we ended up with a new two variable function. Now let's look at a function that's given to us in number 14 on page 937. And number 14, we're given the function f of xyz is equal to zxy plus x, and we're going to find the following. Part A, we're going to find f of negative 1, 2, 1. And that is going to be, we're going to replace x with negative 1, y with 2, and z with 1. And so we're going to have 1 times negative 1 times 2 plus negative 1, which equals negative 2 plus negative 1, or negative 3. So that's an example where we plugged in three real values for x, y, and z. Notice that the range of this function, the result coming out, is just a single real number. Alright, part B. Let's look at f of x plus y, x minus y, x squared. This is sort of a way of writing a composition of functions, and but all we really need to think about here is this is our x, this is our y, and this is our z. So for this formula, first we multiply z, so x squared, times x, so x plus y, times y, which is x minus y. Then we add that to x, which is x plus y. And if we want to, we can simplify a bit. So we have x squared times x squared minus y squared plus x plus y. Or another way of approaching this would be to factor the x plus y out. It really depends on what your intentions are as far as what you're trying to find about this function. Alright, now let's look at another one, part C. F of xy, y over x, xz. So again, referring back to the original function, we have z times x times y. So third coordinate times first coordinate times second coordinate. It's going to be xz times xy times y over x, plus first coordinate, so plus xy. Alright, this time I'm going to simplify by factoring just so that you can see one that works out that way. Again, it just depends on what you're going to want to do with the function, which form will be more convenient for you. But in this case, let's go ahead and factor out the xy, and that's going to leave xz times y over x plus 1, which equals xy times zy plus 1. Next, we're going to look at problem number 16 at the end of section 14.1. In this, we're given 4 functions. Each of them is a 3-variable function, and we're asked to find a composition. And so we just want to go over the notation. It works exactly the same way as it did with single variable functions. So g of xyz equals z sine of xy, and u of xyz equals x squared z squared. V of xyz equals pi xyz. W of xyz equals xy over z. And here we're asked to find g of u comma v comma w. And so all we're going to do is anywhere that there's an x in our original function z, we're going to plug in the function u, which is x squared z squared. So let's make a note of that. Alright, so our first component of g is just going to be the function u, which is x squared z squared. So I've written it here. Our next component of g, our coordinate I guess I should say, since we're not talking about vector valued functions, our next coordinate of v is xyz is pi xyz. So we're going to take this pi xyz here, and we're going to put it in for the second coordinate. So here's pi xyz in the second coordinate. Now let's move on to the third coordinate. So the third coordinate is going to be whatever w is equal to. W is equal to xy over z. So we're going to put that in over here. So here's xy over z. Alright, so all we've done at this point is replace the function u with what it's equal to, replace the function v with what it's equal to, and replace the function w with what it's equal to. Now let's plug into the formula for g. So first, in the formula for g, we have z, which is the third coordinate xy over z. Next we have sine of xy, so the first coordinate times the second coordinate. So here we have sine of the first coordinate is x squared z squared. The second coordinate is pi xyz. Simplifying a little bit, we have xy over z times the sine of pi x cubed, y, z cubed.